Okay, it is the appointed hour, and got to start class. So how are we doing so far? Anybody have any questions about anything before we go on? So not everyone's here. I'll ask this again, but I wanted to know if you want to take the test, the final at the testing center, let me know. I went and walked over them and talked to them, and they said it's not too bad. Has anyone ever taken a final at the testing center here before? Is it crowded, or is it what Jesse said? It's not bad? Yeah. So.
Depends on the time, really.
Mm-hmm. So, your hair's cut?
Oh yeah, fun.
So yeah, if you want, it's the slotted time is it's like Wednesday, I think at 2 p.m. So we can talk more about the final later. But I think I know we'll have time to review. I might be able to finish all the materials in the course today. I thought then we can. I'll just. I've been thinking about what to do. This is what's that? Oh, so I was thinking I'll finish the stuff today. If not, then on Monday, and then we can just go over the first two midterms then each of the Monday and Wednesday to help you review. So, or I can drag this on for as long as I want because I can talk forever. But I'm not going to do that to you guys. I think I will drag this on. No, I make your time as valuable and worthwhile as possible. Okay, so going back to the material. So we're still in electrochemistry right now, and we've gotten through. We left at the end with the Nernst equation. That's with the non-standard condition. So when we talk about batteries. I'm sorry, talk about batteries. So what other applications do we have for electrochemistry? And one of them is the electrolysis of water. So you can take water and you hook it up to a battery, and this is sometimes referred to as an H-tube apparatus because it's in the shape of an H. So I bet you can guess what a U-tube apparatus looks like too. So this H-tube system, and if you hook it up to a battery and you have water in this, you can crack water into hydrogen and oxygen. And the hydrogen goes to the anode, the oxygen goes to the cathode. I'm not going to go backwards, I'm sorry. No, this is right, I'm sorry. Oxygen is on the anode, hydrogen is the cathode. And the hydrogen balloon is generally twice as big, at least in volume, than the oxygen. So, not surprising there. This is not where we get hydrogen. So at least for industrial use. The primary way we get hydrogen for industrial use is using this method here. That is known as steam reformation of methane or natural gas. So this is by far the cheapest way to do it. Take methane and react it in a vessel with water to form hydrogen and carbon dioxide, or it depends on the way you tweak. You can form hydrogen and carbon monoxide as well. So just depends on how you make the process. So this is the majority of how hydrogen is made. The other way that we make hydrogen is in the reformer section of a refinery. So I think I told you that the thing that we make the most of in terms of chemicals are transportation fuels. And the cyclized aromatic compounds, so the most hydrocarbons tend to be straight chained, but you can cyclize them and they have higher octane ratings. And when they are cyclized, when the hydrocarbons are cyclized, they emit hydrogen gas. So that's more of a byproduct, but we can get hydrogen that way. But I mean, when hydrogen is made, unless you're doing a classroom or small scale thing, this is the way it's done. Like the hydrogen they put in the Zeppelins in Germany, made this way. When we make hydrogen to make ammonia, make it that way. For hydrogen for rocket fuel, made that way. So the electrolysis of water is not used typically to make hydrogen, but it can be. And this is the thought for this is maybe electrolysis is one of the options for something like wind energy. So wind energy is just not consistent and can put surges and also no current into the grid. So how can you make wind more useful? Maybe use the energy to crack hydrogen or crack water to form hydrogen, and then collect the hydrogen. Where this is used and used quite extensively is on nuclear submarines. not necessarily for the hydrogen, but for the oxygen. So a nuclear sub, and also the nuclear reactor in a sub, it's only about this big. It's only like 1 or 2 liters. And they use weapons-grade uranium in it, so it's really tiny. And but the Navy, the sailors need to breathe. So how do they do that? Well, you're in the ocean, they crack water. And the hydrogen they just dump in the ocean, and it's usually deep far enough that the bubbles tend not to get away. I asked them about that one. Well, can't you see the bubbles? Like, well, they dissolve pretty quickly, especially at depth. So the hydrogen dissolves in the water, and then the sailors breathe the oxygen. And so nuclear subs, though, they tend to stay. Usually, food is the limiting factor on nuclear subs. So the reactors run for a while, and it's just they run out of supplies. Okay, so next topic. How are we doing? So anybody have any questions with electrolysis of water? Okay. Electroplating. So if you go to places, I remember like one of my first serious girlfriend in high school, for Christmas I bought her some gold earrings for like $15 at the Target. You know, they're not solid gold. They're electroplating. So you can buy cheap jewelry, sometimes electroplating. And typically when you electroplate, use the noble metals, the not reactive metals, things like gold, silver, platinum, that kind of thing. And this is the way they do it. So one thing about electroplating is that wherever you stick the wire, there's a problem. I remember I was in a fraternity in undergrad. My fraternity brother, he was so excited about his girlfriend, like it was a gold colada ring. So, and I was like, well, how much you spend on it? He's like, $20. I'm like, well, you know, it's probably got a wire, it's electroplated, and it had like a little jewel on it. I looked underneath where the jewel was going to be, and I was like, oh yeah, I could see that there was a spot there. It was basically gold-plated copper. I told him, like, well, you know, what's going to happen is you're going to get corrosion along the edges, and her finger's going to turn green eventually. But I don't think they made it, so I don't think she'd be too pissed off yet. So, but so electroplating. Where else is this used? We don't have too much here in Maui, but if you go to the mainland, there's lots of trucks. They have like the real pretty chrome color on it. So the way they do that is they electroplate that when they take the bumpers and whatever, the mirrors, and they coat them first in nickel. So they put a pretty thick coat of nickel on them first, and then they coat chromium on it. So that's where the real chrome, the shiny chrome plated looking things. It's actually nickel then with a layer of chrome on top of that. If you don't put the nickel, you get corrosion along the side. It's like a sheet, and the sheets fall off. But anyways, let's talk about how silver plating, how any kind of metal plating works. You put the metal in solution, and the solution already has this in it, but you also put a hunk of metal, so if it's silver or gold or whatever it is you want to plate on there. And then you hook that up to the cathode, it's the anode, because the anode corrodes. I keep on looking at the positive side, I think, of the cathode. The anode corrodes. You put the noble metal in here, and there already has to be a solution of the metals and the ions on solution. Then you put whatever it is you want to plate in there, and you attach a wire to it. And then current is run through the system, and then the anode corrodes, the cathode grows, and then the noble metal is plated onto the other metal that's electrically connected. So this is really just an image. What they typically do in this, so the low-tech solution to this, because if you put a metal, like if you did this and you had a wire in here, you would silver plate your wire. So what they typically do is they use wood. So wood is the frame, or something else like PVC, polyvinyl chloride, something that does not conduct electricity. And of course the wire is going to be coated in plastic. Otherwise you're going to get a really expensive thick wire if you leave it in there for a while. These solutions are also extremely caustic. So so silver, you can get it to dissolve in nitric acid. But gold and platinum, you have to use aqua regia, which is a very concentrated acid. So you can buy gold plating kits, and it's got basically gold dissolved in aqua regia. If you stick something in there, it'll just plate the entire thing. But if you ever do that, be sure to wear safety glasses because one drop of that will blind you, at least in your eye.
Have you ever played anything?
Yeah, I have.
Some household object?
No, not a household object, just something small. But it's
That's weird.
it depends on if you throw a metal spoon into silver nitrate, like it'll plate it, but it's kind of soft. I've never done it with the electricity. I guess I did it once when I was in grade school, a long time ago. But we used copper. So, but it's a copper sulfate solution. But you can plate many things, but it tends like at least when I did it, I didn't do it very well. Let's just put it that way.
It's like polish it after.
I don't know the process. I've never tried it myself. So I'm sure. I mean, obviously, there's a way to do it because, like, I mean, you can buy lots and lots of silver. There's silver-plated silverware, right? And there's lots of gold-plated jewelry. I mean, and it's fairly robust, right? And when I did it, it was really kind of soft. I don't know long answer short, I don't know the procedure that they did exactly, but they did it much better than I did. Why, you want to start? You want to gold silver plate something? Yeah. Just wear your safety glasses. Okay. All right, so let's do some math on this. And there is a problem like this on the final. But okay, so you can plate gold by this process. Gold plus 3 ions plus 3 electrons makes metallic gold. What mass of gold is plated by a 25-minute flow of 5.5 amps of current? So these are actually really easy problems. Okay, so it's dimensional analysis just like in 161. So an amp is a coulomb per second, so 5.5 amps coulombs per second. And then a 25-minute right? So then the seconds cancel, and then use the Faraday's constant. So mole of electrons, 96,485 coulombs. So that's Faraday's constant, and then mole gold to 3 moles electrons, and I'm getting that from the equation there. That's where that step is. And then, what is the atomic mass of gold? I'm going to say 179. Let's see how. 197. Close. 197 grams gold per mole gold. So, of course, you can see with the dimensional analysis, the units all cancel. So minutes cancels, seconds cancels, coulombs cancels, moles electrons cancels, moles gold cancels. Right. So but do you see the parts? So this is the current. 5.5 amps is 5.5 coulombs per second. We're giving 25 minutes, 60 seconds per minute. Mole of electrons, it's Faraday's constant. Mole of gold, I put silver, shoot, it's AU. Did I say it for gold? Yeah, it is. Sorry, I put silver, it's gold. And that is the atomic mass of gold. At least the internet's catching all my mistakes now. I didn't make mistakes till I started recording the lecture. Anyways, yeah. And the last step is just from the periodic table. And then you just throw it into your handy dandy calculator. 5.5 times 25 times 60 divided by 96485 divided by 3 times 197. You get 5.6. And that's grams gold. But this is usually pretty straightforward. Students tend not to have too much of an issue with this. Anybody have any questions about how this works? Okay. Let's see if we can do this one then. Oh, I should probably tell you the molecular weight of silver. Silver is 107.87. And Faraday's constant, 26,485 coulombs per mole electron. Is anyone getting stuck? Nope. Everyone seems to be looking at his or her calculator. So very, I guess I never thought of this. There's a lot more males than females in this class. Yeah, and we're down Chantel too. Usually 50-50.
I'm back in the like one girl and 30.
There's actually more females than males enrolled in Mountain College.
Well, it's different here for sure.
I'm an undergrad in this chemical engineering. We started off 50-50, and then we had more females change majors near the end. But Cindy Crawford, you know the supermodel Cindy Crawford, she started out as a chemical engineer. Of course, she didn't complete a degree, but nope. Anyway, so how many think it's A, B, C, D, E? Okay, everyone's going for E is right. So I'm assuming everyone.
What's the F thing?
There's no. Oh, that's Faraday's constant. Has anyone ever heard of something called the nerd test before? That's like they ask you questions. I guess it's something like, how many of these constants do you know? And one of them is Faraday's constant, so that your nerd factor may increase me say, take this class. Okay. So, everyone gets that, so I'm just going to move on. So this is how, if you ever wondered how they get stuff like sodium metal, well, sodium metal is a lot of fun to play with. If you haven't played with it before, if you throw it in water, it explodes. And you can do things like you can make a snow volcano and put sodium metal, and the volcano will catch on fire, and things like that. So it's the alkali metals are a lot of fun to play with. It's although it's kind of dangerous. The way that they isolate these is also by electrochemistry, and what is done is, well, this is the way we do it now. I should say the way they used to do it. Well, this will make bleach. It'll make chlorine gas at least. But if you pump the chlorine through this solution, it'll turn to bleach. Bleach is sodium hypochlorite NaClO. But the way that if you take the chlorine out, you get sodium hydroxide, so caustic. Sodium hydroxide is also sometimes referred to as caustic, also sometimes referred to as lye, Lye. Have an aqueous solution, you can put an anode and cathode, and you can connect it up, and then chlorine gas will come out the anode. You can also take just plain old salt, sodium chloride salt, and melt it, and also similarly hook it up to a battery, and if you do that, you get sodium metal will form on the cathode. The cathode grows, and anode chlorine gas will form, and so that's how you form sodium metal. And you can do the same thing for potassium, like put potassium chloride to form potassium. It doesn't have to be chloride; it could be potassium bromide, it could be any salt. And you can break the salt. You have to melt it though. It takes a lot of energy. Melt the salt, hook it up to a battery. And then the metal will form in the cathode, and then the anode will depends on whatever the other thing you have. Iodine would just form solid iodide. It wouldn't. And that'd be a little harder because it would cluster on it. You have to scrape it off. But the gases just fly right up. So fluorine, chlorine comes right up. Of course, they're both highly reactive, fluorine and chlorine, so they can be problematic that way. But that's how we make the things like sodium and potassium metals. And this way, as written, this is how we make bleach now. So it's one of my chemicals of choice. My wife teases me, like, because whenever something happens, like, I'm a chemist, so I get, like, whenever there's something that happens that involves, like, well, I'm also an engineer, so fixing things or anything that involves a stain or cleaning something off, and like, well, how do I get rid of this this mildew? I'm like, spray it with bleach. Like, I was chopping cherries. How do I go with this red stain? Like, bleach. She's like, that's your solution to everything. I'm like, that it is. That it is. How do I disinfect that? Bleach. I buy something new from the store. Like, I got a water bottle. What's the first thing I do? I throw bleach on it. Unless it says not to throw bleach, then I throw vinegar. So, anyways, I like bleach. Use it in laundry. Good stuff. And I go swimming a lot, so I swim in a solution of bleach all the time. Okay, so toothpaste. Close. I actually tried bleach once, and that hurt really badly. So I was curious, so I tried it. I was like, "Whoa, that hurts." All right. So bad idea.
Very.
So I brush my teeth with a little bit like a pea-sized amount. Supposedly, they say a pea-sized amount of toothpaste is all you need, and then I use baking soda. Because my dentist told me that it changes the microbiome of my mouth if I do that. I don't know, but I just do what I'm told. I'm really bad at biology, so you can talk to Professor Irwin about that. She might have a few things to say. But okay, last topic in electrochem, corrosion. And corrosion is a $1 billion per year problem, billion with a capital B. And things corrode, especially iron. And this is how iron rusts. And Uh, the metal itself is the anode. The anode corrodes, and also, if some of you probably noticed that when iron is wet, it rusts. Why is that? Because then the water droplet that is around it becomes the salt bridge. And then the oxide is the cathode. The cathode grows, the metal is the anode corrodes, and then it turns from iron to iron oxide, iron 3 hydroxide. Depends on whom you talk to. But, well, the iron 3 hydroxide is kind of black colored, but it can be a mixture of iron 3 oxide, also iron 3 hydroxide. And it's a big problem. So how do you prevent iron from rusting? You keep it dry. That's one thing. If it's always dry, it won't form the salt bridge. It won't corrode, at least at the surface. Except for the surface. What else can you do? Sacrificial anode. So typically, the sacrificial anode used in iron is zinc. So if you ever wonder what galvanized steel is, have you heard of galvanized steel, galvanized nails? It means it's coated in zinc. So the zinc is more active than the iron. It gets corroded first. That's what it means, sacrificial anode. One of the anodes, it's sacrificed to save the other metal. And one of the things my wife and I did for, like, we actually have 2 sets of wedding rings because her father insisted on buying us wedding rings, which was okay, that's cool. But she's an astronomer, so I got meteorite rings. And they said, "Whoa, do you want to have platinum or do you want titanium for your meteorite rings?" And without it's going to be like titanium, because the titanium would anonically protect the meteorite. The meteorite is iron nickel. So the titanium would be the sacrificial anode, the cheap stuff, sacrificial anode to the cool meteorite. If you put platinum in that ring, the meteor will become the sacrificial anode to the platinum, and then it'll make a corroded. And that's the cool part of it. It's the meteorite, and of course when iron corrodes, it turns brown. So a platinum meteorite ring will turn brown pretty quickly. So if you get one, get the titanium one because it's better chemistry. So if you want a platinum ring, get a platinum ring. If you want a meteorite ring, get one coated in titanium. And so sacrificial anodes, these are used extensively in industry. So things like pipelines. Does anybody know the difference between a pipe and a tube? Anyone ever heard this before? What's that?
I don't know the actual definition, but all I know is that it helps direct something.
Yeah. It's the way they're manufactured. A tube is extruded. So have you ever seen like the Play-Doh things when you put the Play-Doh in and you push on something and then hair grows out of that? You ever seen those? Oh, you haven't. Okay.
No, what? It had some. Yeah, it's a string.
So you're like silly string or something like that. Well, that's something different. But you ever seen you have Play-Doh, you put it into a thing and you push down and then little strings of things come out. Yeah, that's how tubes are made. They're extruded. So you have whatever it is, metal, Teflon, and you push it, cement, and it's extruded just like that thing, and it's extruded through a form. So tubes tend to be smooth. What a pipe is, pipes are welded. So you take a sheet metal and you wrap it around and you weld it as you turn it, and you have a weld line all around a pipe. So that's the proper usage. But we don't use it. That's not necessarily. We use it interchangeably, colloquially. Like you call the tube in the center of the. Actually, I think it's the pipe. You see no, it is a tube. The tube in the center, like toilet paper. You have the tube in the middle. It's not a tube. It's actually a pipe because it has little sheets. You can tear them off. Right. So you're not going to have paper tubes. You have to have a pipe for paper. So, but pipelines. I mean, so these are made like petroleum pipelines. They are made that way. You take a piece of iron and you weld it. You have people welding it as you move, and you do it in a spiral fashion. Made from iron. How do you prevent that iron from being corroded? You every so often
you take a large piece of zinc and you electrically connect it to the pipeline, and you let it sit there. You let it sit outside, or you bury it deep in the ground. Then what's that?
You said so electrically connected?
Yeah, you put a wire. Yeah, that's why you make electric connection. There's current can flow along a conductor. So electrically connect whatever it is you're going to protect against the corrosion, connect to that, and then every so often you go and you just replace the slug of zinc, and they do that like on the order of 5 to 10 years, depending on. Of course, the bigger piece of zinc, the longer you have to go between that. So that's how they prevent there's huge pipelines. There's pipelines underground that run all throughout the mainland USA. There's a huge pipeline bringing natural gas from Alaska down to the Pacific coast. All these pipelines. There's one on Oahu that it's not as big as one on the mainland, but they have buried petroleum pipelines on Oahu. How do they prevent those from being corroded? You attach zinc to it, and then every so often dig it up, replace it. So, and the last thing is passivity. And they do this with iron sometimes. Have you ever seen buildings they're ugly brown colored? I mean, they're metal buildings, but they're ugly brown. The way that they do that is they take iron and they throw it into typically nitric acid. And what happens is it's really reactive. It just reacts really violently. And then after a while, bubbles, it's what's forming hydrogen gas. The bubbles start to go away, and then it doesn't react anymore. And that's it. It's passivated. It doesn't react anymore. It's pacified. So the problem with iron, though, is of course the iron oxide is really soft. I mean, you can chip it off with your fingernail if you wanted to, right? So rust is soft and it's flaky. So they do have passivated iron, but it kind of has gone out of style of sorts. They did it a little bit more in the 70s. So now it's probably more galvanized, tends to happen than anything else, or coat it with something else. Problem with coating iron with other things, you can get what's called pitting corrosion. Cars do this all the time. You get a hole in the paint job, and then you get pitting corrosion where the hole is. So that's very common. And also, if they're ever coated, you can get pitting corrosion. Also, you can get lateral corrosion. So this used to happen to bumpers before they coated them with nickel. So if you just coat a bumper in chrome and not nickel, it tends to corrode along the edges. And there'll be one pit, and then it'll corrode, and the chrome will just flake off. So coating is a difficult endeavor, at least for corrosion. But passivity, and some metals do this naturally. So unfortunately, iron oxide is very soft. Many metals pacify, and what they turn into is harder than the metal itself. So the prime example for that is aluminum. Aluminum will react to form aluminum oxide, and aluminum oxide is the second toughest mineral, naturally formed mineral. First one being diamond. The hardest material known right now, it's debatable whether it's diamond or boron nitride. I've seen people claim both. I don't know which one is harder. But aluminum oxide, also known as sapphire, maybe you can even say it's a ruby. A ruby is a sapphire as well. It's just like a sapphire, like pure sapphire. It's kind of clear colored. It's like glass. A blue sapphire, the gemstone, it's aluminum oxide with impurities of iron and titanium. And a ruby is a sapphire with impurities, sapphire aluminum oxide with impurities of chromium. But they're tough materials. So, other thing with aluminum, maybe you've heard the term anodized before. Anodized aluminum is just a thicker oxide layer. So you can do a process. I don't know what exactly the process is, but it's just a thicker oxide layer, and they also can color it. So think about anodization. It's usually black, but they can color it different colors if they want to. So caution with aluminum. What will go through the layer? Chloride, Cl minus. Chloride will go through aluminum, at least the oxide layer. and can corrode it. So that's why we don't use aluminum for water pipes at all, and we typically don't use it in the ocean either. So because of the chlorine, you can use aluminum boats in fresh water. That's okay, but not in the ocean, not in municipal drinking water. Why? Because most places they chlorinate the water. They chlorinate the water here, actually pretty readily in Maui. Oahu, they tend not to chlorinate the water as much, but some places, if you have spring water, it's probably okay to use aluminum pipes, but most places, they don't even really sell it with the plumbing anyways. The other metal that use, many other metals do this, but another one that's commonly used is titanium. Titanium is also extremely reactive, but it forms a titanium oxide layer. And the other thing about these metals, so aluminum and titanium, they're really hard to weld. So iron is really easy to weld. Aluminum and titanium are not so easy to weld because they can catch on fire. So you have to be very careful if you weld. You can weld them. It's very dangerous to weld them, and it's especially in an oxygen environment. So, but titanium also forms a passivated oxide layer, and what will penetrate that layer is methanol. So if you ever wonder, don't buy a titanium methanol container, but that's probably kind of trivial knowledge for you though. So anyways, that's the end of it. Anybody have any questions about anything? Okay, on to nuclear chemistry then. All right, I don't know if I'll get through this. I think I will. Okay, so nuclear chemistry, last topic. And does anybody remember the 4 fundamental forces of physics?
Sorry, what's the question?
What are the 4 fundamental forces?
Oh yeah, so electromagnetic, right?
Yep.
Gravity.
Gravity.
And the weak and strong nuclear forces.
Yes, there you go.
Yeah, inter and intramolecular.
Yeah, there we go. 4 forces, although some argue 3 or 5 alongside 4. So the idea is the nuclear weak force is actually found to be the same as electrostatic. So electromagnetic. What would you call it?
Electromagnetic.
Oh, okay, yeah. Electromagnetic. And actually, using the gamma function, they connected the two. So one of the things we're looking for in physics right now is the grand unified force. So there's only one force. So you could argue that we know of 3. You could also argue that we know of 5 if you count electromagnetic and weak as different forces, although the same force. The last one being dark energy. We don't know what that is. So, but 3 to 5 forces. But so let's talk about them. Gravity, ever positive, and extremely weak. Weakest force is gravity, ever positive, extremely weak. Nuclear or electrostatic, that's basically unlike charges attract, like charges repel. Nuclear weak, that what binds. So protons and neutrons, for instance, are made of smaller particles called quarks. And what binds them together to form nucleons and other hadrons, as they're called, that is known as the nuclear weak force. Then there's a nuclear strong force, and the nuclear strong force is what binds an atom together. And how we discovered this is when we were breaking apart the atom, we have the negative electrons and the positive protons in the nucleus. And the thinking is, well, you have and a nucleus is pretty tiny. So there's this tiny area where you have a bunch of positive charge. And the idea is you need a force that's stronger than the repulsive electrostatic force to bind the nucleus together. And that's what the nuclear strong force is, or sometimes called the strong force. So the electrostatic force is trying to rip the nucleus apart, but the nuclear strong force keeps it together. And sometimes the nuclear strong force is not strong enough to bind the nucleus of an atom together. And the primary particles that do the nuclear strong force are protons and neutrons. There are other ones, pions, for instance. They also have the strong force as well. But we're going to stick to hadronic atomic matter, so hadronic matter. So that's the idea is that the nuclear strong force, if there's enough force there, so if there's the right number of protons and neutrons together, it can form a stable nucleus, and the strong force will overcome the electrostatic repulsion. So unstable nuclei, we have a special name for them. We call them radioactive. You've probably heard that before. And that was when we were learning about radiation. They found that like uranium they said it gave off uronic waves, and some of these radioactive materials, they found radio waves. Like, wow, we can find radio waves from these materials. We're going to call them radioactive. It's not just radio waves, though. It's much what the dangers are gamma rays and also the other types of radiation we'll talk about soon. So it's kind of improperly labeled radioactive. But the main point here, the unstable nuclei are known as radioactive. So remember when we talked about it wasn't in my class, but in your previous semester, whoever you had it with. I know some people, most people had it with Tibbet, but wherever you had it, the electrons have energy levels, right? So like the 1s, 2s, 3s, and so on, and there's degenerate energy levels. There's 3p's that are degenerate. For nuclear, same rule for protons and neutrons. Protons and neutrons are also fermions, so they have spin up and spin down. But the difference is the energy level differences are huge. Electrons are relatively close together, and there's huge energy level differences in protons and neutrons. And I can tell you that nuclear physics is much easier than chemistry, because when you do calculations on electrons are so messy. They're tiny, they're light, their energy levels are close together, and you get these wave patterns that are really, really difficult to discern. For spectroscopy of nuclear things and for calculations for nuclear things, the energy levels are so far apart, they do not interact at all. And just like electrons, you can have excited states. So there's nuclear excited states, just like electrons, and when they relax down, they emit photons, but in this case, gamma rays. So we'll talk about that with nuclear medicine. That's how bone scans work. It's an excited nuclear state. And also, nuclear chemistry, the numbers are so easy. You have to solve an equation for this, and I'll do an example later, and I have a problem set ready. But the top numbers and the bottom numbers have to equal the same thing. So when you have an element, the bottom number is the atomic number. It's the number of protons, the number of positive charges. The top number is the mass number. It's the number of protons and the number of neutrons. So it's and although the binding energy, the mass of the proton or the neutron, it depends on what environment it's in. Actually, the mass changes depending on the environment, but they're considered equal for the mass numbers. The mass of a proton and neutron is about, we call it 1. A neutron is slightly more massive than a proton, at least a free one is. A free neutron is slightly more massive than a free proton. It depends on what environment the neutron is. Doesn't mean all neutrons are more massive than all protons, but it just depends. Okay, so an example of, so we'll go with some nuclear equations. Oh, and electrons and positrons are considered to have, and photons are considered to be a mass of 0. A bad habit that nuclear chemists and physicists do is they sometimes give masses for things and energy. So do I talk about that? I guess I do later, but you're probably familiar with this equation. Energy is mass times the speed of light squared, so equals mc squared. So we found that mass and energy are interchangeable. Sometimes nucleons and other particles are given in energy. So a proton has an energy mass of about 2 gigaelectron volts, and an electron has a whatever, 50 mega electron volts. So it's about electron energy-wise is about 1/2000th the mass of a proton or a neutron by mass and or energy. Of course, depends on its environment. Okay, so let's talk about the different types of radiation. And just like the Greek alphabet, alpha, beta, gamma, alpha decay is this way. So, and here is a common alpha decay.
Uranium-238, also known as depleted uranium, can alpha decay into thorium-234. It releases an alpha particle, which is a helium nucleus, and a gamma ray. And the gamma ray is a photon. It's a very high energy photon. So whenever there's a nuclear event, gamma rays are emitted. And they're very easy to detect, and it's very easy to find concentrations for things. So, and notice the numbers here. 238 equals to 234 plus 4, right? So the top number is the same, the bottom number is the same. I mean the same as in the same values, on the left and the right. 92 uranium also equals 90 from the thorium plus 2 from the alpha particle. And the gamma ray, it has no mass, it's a photon. It's 0, 0. So top numbers are the same, bottom ones are the same. So you don't even, so the symbols, of course, like U for uranium, the symbols are not really needed. We do that, we usually do that because we like to name things that way, but you could just have element number 92. It doesn't necessarily have to be uranium. We could name it whatever you want. So the more important thing is that it's an element with 92 protons. And okay, so the product is also referred to as a daughter nucleotide. So this is the parent nucleide, daughter nucleide. And alpha particles, so helium nucleus is given off. So depending on the amount of uranium in the soil, some places there's natural gas. Natural gas can contain helium. So if you wondered where do we get helium for balloons, that kind of thing, we get it from natural gas. You refine it, and one of the things that in the refining process, helium is removed. United States natural gas tends to have a lot of helium. Natural gas from places like Russia and Norway tend not to have as much helium as we do. So there's less uranium there. They get them more from the methane hydrates, is where their natural gas comes from. So, but United States, we tend to have a fair bit of uranium in our soil. So not here in Hawaii. We have virtually none, except for on the Big Island where we did simulated nuclear bombs. So there's a little bit in the Big Island, but not on Maui or Oahu or Kauai. I don't know about Kolave, probably because we bombed a lot of stuff there. But okay, so that's alpha decay. Alpha particles are not that dangerous outside of you. So if you're going to be hit by a bunch of alpha particles, not a big deal. You can stop that with your skin or like a piece of paper. Like this plastic bag would stop alpha particles. Okay, so, but alpha particles inside the body are really, really dangerous. These cause the most damage inside the body. Outside the body, not a big deal. Inside the body, really bad news. So radon gas. So radon gas, when you inhale it, of course, Hawaii is nice. We don't have that much radon at all because it's a byproduct of uranium. So we have very little radon gas in Hawaii. But radon, if you get into your lungs, it'll emit an alpha particle, and it's like a pinball machine. Beep, 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 and it goes around and dings a lot of things, and it breaks chemical bonds. That's what the danger is with radiation. Radiation just breaks chemical bonds, and it causes cell damage. And it can cause cancer, by the way, that if it hits the DNA of a molecule, the DNA can be damaged. If the body repairs it incorrectly, it can form a cancer cell. So that's how radiation causes cancer, but it mostly just causes cellular damage. So UV light is radiation. It's an ionizing radiation, and like a sunburn, it hurts. You get a sunburn, you're now thinking, oh gosh, I got cancer. You're like, man, this hurts. So that's what radiation is mostly. It's just mostly damage. So alpha particles the okay outside the body, inside the body, very, very bad. Beta decay, so an alpha particle, alpha decay, drops the atomic number by 2. Beta decay increases the atomic number by 1, and this is done via, so a neutron, which is slightly more massive, can turn into a proton and an electron. So the electron, this is a symbol for electron. So neutron has one mass, no charge, forms a proton, 1 mass, 1 plus 1 charge. Electron, we consider it 0. It's about 1/2000th, but it's 0 and minus 1. So 1 plus or minus 1 is 0. So top numbers is equal, bottom numbers equal. A beta particle is a high energy electron. And beta particles are relatively not that dangerous. They tend not to go very far. Where they are a danger is to your eyes. So beta particles can cause cataracts. So survivors of nuclear blasts, some of them get cataracts from the beta particles coming from the nuclear explosion. And this can be blocked by a thin sheet of metal or a block of wood. So this could block a beta particle. Also, plastic is pretty good. So or glasses. Your glasses will protect you from beta particles. Gamma, though, it needs a lot more. Gamma needs a couple feet of lead or a couple meters of concrete. So you need quite a bit, like 10 feet is pretty standard. So like a nuclear power plant, you see they have like the hyperbola. They coat everything in concrete to keep any of the radiation stuck inside there. One other thing with beta decay, so one thing you do not want to do is you do not want to use a thin sheet of metal, like especially so or lead. Like it depends on how thick the metal is. A thin one is bad. A thick one is okay. The reason being is that beta particles, high energy electrons, if you shoot them toward a metal, what happens is that the nuclei of the metal bend the electrons, and as the electrons are bent, they emit X-rays. So if you have too thin of a piece of metal, you can then generate X-rays, which are also ionizing radiation. So you can actually be better just to keep the beta particles and then having to deal with the X-rays. But I mean, this solution is easy. Just make a thicker piece of metal. So don't, like, if someone says, oh, it's beta decay, like, don't go grab a bunch of sheets of aluminum foil. Have a little thicker. So something something about as thick as a pot, like a pot or a pan, that'll stop the beta particle. So, but a piece of aluminum foil, that'll generate X-rays. So that's how they generate X-rays at like the dentist's office. They have a beta source and they shoot the electrons, the beta particles, towards a piece of aluminum or copper, and then as it bends it, it'll generate X-rays, and then they use that to look at your teeth. Or same thing with, like, for your bones too. That's how the X-ray machines work. Okay. Other ways that can happen, the positron emission. So maybe you've heard of a PET scan before. This positron emission topography. They use this to image your brain. So you can put glucose, sugar that has carbon, has a really light form of carbon, and it can give off positrons. So a proton can turn into a neutron and a positron. So that electron with the +1 charge, that's known as a positron. That's also known as antimatter. So what is antimatter? Antimatter and matter are very similar, except antimatter has the opposite charge and the opposite handedness of the spin. So an electron, for instance, so the spin up, spin down. The idea is an electron has its magnetic moment, so it all of it sums up into like a right-handed spin up. So, and we call it right-handed just because we have a right-hand system. A positron would have its positive charge swirling around, but it goes in a left-handed. I guess you haven't learned that about right-handed, left-handed systems in math yet.
So has anyone ever gotten there? No? Okay. So the x, y, z axis is like this. So this is x, y, z. And the reason why is the x-axis is pointing at you. You curl it towards the y-axis. The z is up. Like that's a right-handed system. Okay, so that means antimatter. Antimatter then, if you do it that way, it's going to be, so x curled to y, we'll have it pointed this way. That's the other-handedness. It'll be going down. So electrons and positrons are different by their handedness of their spins. So you guys, some of you are taking whatever, E&M. So you learn about current through a wire. So you run current through a wire, and the current's moving this way. The magnetic field goes this way. If you ran positrons through a wire, I guess this way, your magnetic field will go the other way. So if the positrons are moving this way, or the current, I guess the positrons are actually moving this way. Actually, no, I guess with the current, I guess it would be. Yeah. But anyways, it would be left-handed instead of right-handed. So that's what I mean by handedness of spin there. And then the charges are opposite. But when matter meets antimatter, they annihilate each other and turn into energy. So that's the other consequence of matter and antimatter. And for whatever reason, the universe, this is one of the things that we don't entirely understand. The universe, as far as we can tell, is at least it's got much more matter than antimatter. We haven't been able to find large amounts of antimatter anywhere. Matter is by far preferred over antimatter, and we don't really know why. Okay, but so here's the summary of the different types of radioactive decay. I guess you can't see that. I'll have to zoom in even further. So we have alpha, that helium nucleus is emitted, and you lose mass of 4 and 2 positive charges. Beta decay, basically no loss in mass, but the atomic number increases by 1. Gamma, this is an excited state. Energy is given off. Positron emission, turns a proton into a neutron. So the atomic number goes down, but essentially no increase in mass. And and then the last one, electron capture. Electron can be captured. Sometimes, if you look into some books, this was referred to as K capture, and that's from German for Kern, meaning first. So first, it's usually the 1s electron that's captured. You can also do K capture, electron capture. A proton can absorb an electron to form a neutron. So electron capture is another one. The more common ones are alpha and beta decay. The positron emission and K capture, electron capture is not as common. Okay. How are we doing so far? Anybody have any questions? So I thought this stuff was really cool, so I started out grad school as a nuclear chemist, and I changed to physical chemistry. I started studying lasers. I changed because a nuclear chemist, it takes 8 years to get a PhD, and then it locks you into a certain pathway job. But to be a physical chemist, there's lots of jobs for physical chemists, and you get a PhD in about 5.5 years. So I was like, well, do I really want to spend an extra 2.5 years doing something that I'd be locked in a job and I really have lots of interest? So nope. So I changed. But I know a lot of the stuff. So probably puts me on some sort of watch list because I know a lot of nuclear stuff. Anyways, okay. So let's talk about the value of stability. I wish we had a chart like this for people. Just have one for nucleons. Okay, so the x-axis here, number of protons. Y-axis, number of neutrons. This is the y equals x line. So something to note is the number of stable elements
And the yellow stuff, the dots are stable. The yellow are metastable, sort of stable. They're radioactive. And the other ones outside, they don't bind together even for a nanosecond. They just fly apart. But the stable ones, you can see they start to increase and they go up. Why is that? Well, as you get more positive charge into the nucleus, the positive repulsion, it gets bigger, so you need more neutrons. The neutrons provide the strong force, but they don't have a charge to them, so the neutrons are kind of like glue, and they stick the more massive nuclei together with the neutrons. And so just like in chemistry, like in normal electronic chemistry, we have sort of magic numbers. The magic numbers are 2, 10, 18. Is it 96? But they're these numbers on the periodic table. Yeah, 18, 30. So the magic numbers are 2, 10, 18, 36, 54, 86, and 118. Those are also known as the noble gas configurations. Those are extremely stable states for electrons. Nuclear stuff has the same idea, but the magic numbers are 2, 8, 28, 20, 28, 50, 82, 126. And even of those, the more stable one is 28. So the most stable element, nuclear-wise, is iron. Iron is by far the best. Okay, so that's the reason why some stars explode. Okay, radiation detection. This is probably bad from a James Bond movie. What is it, Dr. No? Anyone ever seen Dr. No? Okay, it's even before my time, but I like James Bond. They improperly call them radiation shields. The film badges, maybe you've seen people wear them. They're a square thing about this big. They're typically gray, and you can wear them here, sometimes here. Those are film badges. Sometimes people wear them as rings. So you're allowed to get a certain amount of radiation. Your whole body, you're allowed to get 5 rem. We'll cover them later. If you get training, you're allowed to get 10 rem. Doesn't mean anything. Just means that they'll let you get a little more. At least the U.S. government will. I don't know the numbers, but your hands can get higher dose of radiation. You have a question? It's a Rotogen something man. It's a unit of radiation. I'll cover that later. And okay, so film badge, that's one way. It does the overall dose, and it's averaged over a period of time. A Geiger-Muller counter. This is also known as a Geiger counter. It's a tube that has a gas, usually argon, in it. And then when radiation goes through, ionizing radiation, it'll ionize the argon atoms, and then you have a detector there. The ions then hit the wire, which detects them, and that's where the clicks. So you're seeing a Geiger counter click, 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 click kind of thing. Those are the counts of the ions hitting the detector. And so that's a Geiger counter, Geiger-Muller counter. And the last one is a scintillation counter. Uses the salt, sodium iodide or cesium iodide, and when radiation hits that, it'll generate ultraviolet light, and then the light is then detected, and then the radiation is monitored that way. So these are the ways we can measure radiation. Of course, for radiation workers, film badges are used very frequently to find radiation. Geiger counters are used very frequently. For doing studies on radiation, the scintillation counters are used quite a bit. Okay. Oh, what's that?
That accident that happened in Brazil
I don't know about that.
in 1987. Someone from like a radiotherapy place started capsules containing sodium, not sodium chloride, cesium.
Okay.
And the guy that worked at like the old metal sorting facility.
Uh huh.
He thought it looked cool, so he brought it home to his family and passed it around. And ended up killing, contaminating 600 people in 2011.
Oh wow.
And yeah, it was terrible.
It was from the cesium iodide or something.
Cesium chloride.
Oh, cesium chloride. No, okay. Cesium is probably cesium 131. It was
137.
137. Okay, let me. Do I have this stuff about? I don't have the different types of radiation. Okay, so the depends on the unit. There's radiation units. There's a Curie. There is. Let me see if I can find it. Curie is how much, just simply how much radiation is released. How many counts. Then there's rad and rem. Do they have that in here? And there's a sievert. A sievert. Okay, they don't have that. Okay. Yeah, okay. Rem is Roentgen equivalent man. And that's what it is. I don't see it in the book. I'll have to tell you next class. I know that there's the Curie, just has how many, that's how many actually break apart. There's the rad and the rem, they're similar. And then there's a sievert, and that's connected to it's basically a rem times a certain amount of time. Like one sievert, I think, is one rem, or maybe it's like, maybe it's 100 rem. Shoot, I don't remember. Okay, I'll have to get back to you on that one. But I can go ahead and skip to this. So this is a radiation exposure for things. So a 5-hour jet plane ride is about 2.5 millirem. You're allowed to have 5 rem per year. Your question?
Sorry, just really quick. You know those lead vests that you wear whenever they like a tooth X-ray
Yeah.
or a dental X-ray or whatever? What is that made of?
Lead. It does absolutely nothing.
Or not like never mind. I thought
It's like little. Lead's a very soft metal. Besides that, but it's just like little pieces of lead and plastic. They do absolutely nothing. Because X-rays go in straight lines. Like you remember, you have a cone. Like imagine instead of a X-ray machine as a flashlight, and like I always argue with the dentist. They're like, I'm like, this does absolutely nothing. Like, yes, I know, but put it on. Like, all right. Can you imagine if you have like a machine here, you turn a flashlight on, what's going to happen? Light's going to go like this. What's going to happen to the X-rays? Same thing. And if I have, if I'm getting my tooth X-ray, does that mean it's going to go towards my gonads? No, it's not. Right? I mean, do I really need to have a lead vest over my crotch to get a dental X-ray? You do not need that. Yeah, I mean, one of the things I would do if I was a technician doing that, I would, slink away. Because, I mean, if you keep on getting exposure over and over again, you can cause problems. And you think that X-rays cause bone cancer. They can. What dentists used to put their fingers, like if you're like, all right, well, here, because you know how they make you hold the thing and you're like sitting there like, is this the right part? And you're like, and you have to hold it. It used to be the dentist that did that, and because of that, dentists used to have kind of manky-looking fingers from the X-rays, right? Because their fingers, if they're holding it here and then the X-ray is coming, like the tips of their fingers are going to get skin cancer and just look kind of messed up. Glenn Seaborg, atomic chemist, apparently his hands were really ugly. I never met him. He died before I came to Berkeley. But he, like dentists and some of the old nuclear workers, their hands get all kind of messed up. And I think that's one of the reasons why people hate dentists. At least they like in the past. Oh, dentists! So like one of the things like they have really messed up hands from the X-rays. But But X-rays, I mean, as long as you're getting them occasionally, they're okay. So, but jet airplane rides, so you get 2.5 millirem per trip. This only works if you fly during the daytime. If you fly at night, you don't get as much radiation exposure. So you can get that from the sun. And you get some also from cosmic rays. It'll be a little higher. When you go up, it'll be a little bit higher, but not that much. So cosmic radiation from space, you get that. Everyone gets that. We get that here. Can you read that? I guess, I don't know if you... So terrestrial radiation. So that's from the Earth itself, most specifically from radon and thorium. So that is essentially close to zero for us here in Hawaii, because the igneous rock that we're on has a very, very small amount. It has some, but has very, very small amount of uranium. Nucleotides in our body, so the carbon-14 and small amount of tritium that we have in our bodies and other radioactive nucleotides, we get a little bit from that. Radon gas, varies, 200 millirems. Depends on where you're at, you can get more. So here in Hawaii, of course, essentially zero. Other places like where I grew up in Ohio, and I know my brother and sisters who live in Chicago, Milwaukee, they have to do this. Whenever you, like for houses, you can have a radon detector. We don't basically don't have radon here, but they have a radon detector in the house. Especially if you're going to sell it, they make you, one of the common things, to do a radon test. And it's because if there's not proper ventilation, radon can accumulate in houses' basements, and that can cause lung problems. Okay, chest x-rays, that's about 8 millirem. So remember, you can have 5 millirems, so that's 0.008 rem. So that's a lot of chest x-rays, right? So don't be afraid about chest x-rays. Dental x-rays, so those can be pretty hefty, right? But I mean, it's not that, I mean, you get them once or twice a year, not that bad. I'd be more afraid of cavities. I guess I'm not super afraid of radiation, but where you get a huge amount is in CT scans. Do they have a CT scan? Oh, they do, right there. Okay, so mammogram. Of course, I don't have to worry about that, but that's a little bit more X-rays. Barium enema. I've actually had this done to me. At least I don't know if it's necessarily the enema, but the when you have to drink. Has anyone ever done this before? Have a CT scan, you have to drink the barium sulfate, and they use it as a contrasting agent. I'm the only one that had this done. Okay, so what they do, you drink barium sulfate, which tastes terrible, and then they bring you the CT scanner. It's basically a big donut, and you're on a whatever table that goes.
Yes.
Yeah.
I didn't take the barium.
Yeah.
Oh, you didn't? Okay. Did they give you? They weren't using your stomach then.
They went to my stomach. They were doing my chest up.
Okay.
Just to see if I had cancer.
Oh, really? Did they give you the iodine contrast?
Yeah.
Yeah, I had the barium and the iodine, and yeah, and it's over fast too. And I mean, that's about 400 millirems, so that's a hefty dose. A whole body dose is about 1 rem, 1,000 millirems. So you probably maybe a little less than 400 for you, maybe 300 to 350 millirem for that. But I mean, some people, they do the entire body, and like MRI, like have you ever had an MRI? I hate MRIs. Yeah, they are so super safe. I mean, you could live in an MRI machine and you'd be fine.
They're boring.
Yeah.
Like 30 minutes.
Yeah.
And they give you preset music.
Yeah. And I've had 2. One I was freezing, the other one I was hot. So it's like I haven't quite figured it out yet. But like, I mean, CT scans are so quick and easy. You're in and out. But they use X-rays. And so building materials. We okay. There's other things. I've had a bone scan. Oh, it looks like time's up. All right, my shut up alarm. I'll finish this up on Monday. It won't be that much time. So, okay. I better get out of this one.